Now that we've covered the user interface in depth and the basic workflow of particle flow, let's have a look at some other concepts that are important. Some things to bear in mind when working with particle flow is the concept of channels. Channels are simply containers that are used for each particle to store information about it. As I said at the beginning of this tutorial, particles work by being as light on data as possible, and this should be borne in mind when working with particle flow. As an example, the particle's position is a channel, its ID is a channel. If you add a material to the particle, this adds a channel. If you assign a material ID, this is also a channel. So as you can see, it's very easy to quickly load up your particles with a lot of data, and this data has to be stored per integration step for each particle, and this can quickly become an issue in a system with millions of particles. So, what can I do about this? Well, quite simply, always be aware that new operators can add new channels to your particles. Sometimes this is totally necessary and cannot be avoided. On other occasions it can. So, where possible, avoid adding extra channels of data to your particles when your final goal is to have a large number. This becomes a major issue when you have to cache your particles, as their memory overhead can be a very real problem. Of course, if you're planning a flow with low numbers of particles, you have the luxury of not really having to worry too much about adding any extra channels. Bear these points in mind when you're working with particles. Another thing to bear in mind whilst working with particles is that particle flow will apply the actions in your flow to the particles at discrete points in time. These samples are called integration steps. The most standard sample point is at the end of every frame of an animation. This means that in PAL you're getting 25 updates per second, whilst in NTSC you would be getting 30, and of course with film you'd be getting 24. Now, although this may seem like a pretty frequent update, there are certain circumstances where it's not enough. The most common example is with collisions and fast-moving particles. As a fast-moving particle could be moving in real terms at, let's say, 2 meters per frame, and as it approaches a surface, it could collide with it. It would get within half a meter of the surface at the end of a frame, and in the next frame, it will move another 2 meters, and then particle flow will test for a collision. But it'll be too late because it will have moved through the surface already. So this can be quite a big problem. Let's have a quick look at a file which I've prepared to look at this. I'll just press play and show you what this particular example does. Now you can see that the integration step on this particular particle flow is not producing a good result. The particles are flying through the air. They're supposed to be colliding with the sphere, and they're not doing it at all. They're just passing straight through. So how can we remedy that? Well, we can go to the global icon, the source icon, and as I discussed earlier, in here you can see you have values for the integration step for both the viewport and for the render. So you can see that currently it's set to frame for both. So what I'll do now is I'll change the viewport integration step to half a frame, and we'll press play again. You can see that the feedback is still pretty good. It's still playing back at pretty good frame rate, but now you can see that the particles are actually colliding a little bit better. It's still not very good though. If we do so again, we'll put down the integration step to an even finer detail, 1/4 of a frame. You can see particle flow is updating the flow up to this event. And now if we press play, you can see it's got a little bit better again. More particles are colliding and they're being pushed along the surface, but it's still not great. So let's increase it to 1/8 of a frame. And then we'll just press play again. And you can see it's actually much better now, but it's still not perfect. So if we carried on in this manner, we could actually get a much better result in the render than we can get in the viewport. In the viewport we're limited of going down to 1/8 of a frame as the maximum integration step. Whereas if we look at the render time values, you can see that we can go all the way down to 1 tick. There are 4,800 ticks per frame. So that's a very, very, very fine value, and generally you wouldn't want to go that low. So in this case, a much better solution if we have a look at the particle view. And in this case we can see that the integration step isn't necessarily the whole problem. What we have here is you can see the particles are born, then their position is set by a position icon operator. Then you can see they're given speed, which makes them fly through the air. And then you can see they're detected to see if there's a collision with the surface. And then a force is applied, which is gravity. So this is a good example of a situation where the precedence of our operators does actually make a difference. Also notice that because I've got the source selected, you can still see the same integration step values here. So you can either change them on the icon in the viewport, or you can change them by selecting the source in the event view. Now, as it turns out in this particular case, it's not so much the integration steps that are the issue, it's the actual order between the collision and the force. What's happening here is the particles are being detected for a collision, and then afterwards they're being forced downwards by gravity. This doesn't really cause a problem when they're flying through the air because the collision doesn't really come into the equation. But once they start colliding with the surface of the sphere, then it does become an issue. And basically the force being applied after the collision causes the collision to fail, because the particles are basically pushed through the surface after the collision has taken place. So what I'll do now is I'll move the timeline back to 0. I'll change the order of these two. I'll just drag this above. And we'll press play again, but I'll change the time steps to frame. Now, we should expect this to be obviously very, very poor as it was originally. But because we've changed the order of these two operators, you should notice that it actually works correctly now. So there we go, we're getting perfect collision detection. And you can see the particles are working just fine. They're falling off the ball and they're landing on the floor. It's working exactly the way we expect. So those are two things to consider in your scene: the integration step value and the order of your operators within your events. Now, that isn't the end of the issues that can come around with integration steps. So let's have a look at another couple of examples that show other issues that can come around with integration steps. Let's have another look at another example. And in this case it's called integration steps noise. Okay, here we have our scene. I'll just press play so you can see what happens here. And in this case you can see the particles go flying through space. Now let's just check what the integration step is on its source icon. You can see at the moment the integration step is set to frame only. I'm just going to bring a particle view and have a look at what we have in action there. You can see that we have two force operators in force. These are using the wind space warps in our scene, which you can see here and here. And they're applying their forces to the particles. Now currently the first wind force is actually turned off and the second wind force is active. So let's have a look at what those two wind forces are set up as like. The first wind force, you can see, is using a scale of 0.003. Now it's interesting that with a wind space warp, the scale value in the turbulence is actually inverse. The smaller the value you go, the larger the effect that the actual turbulence will have on your particles. I don't mean that it'll perturb them more, but I mean that the particles will follow larger curves. If you use a larger value, this means that the curves will become more and more compressed. Effectively, it's like a noise algorithm being projected through space. When you use a very low value, the actual noise changes slowly through space. When you use a higher value, the noise changes more rapidly through space. So you get a more turbulent effect when you use larger numbers. So you can see that the first wind force is using quite a small value and therefore will produce very curved motion of the particles, very large curves. The second wind force is using a much higher number. It's using just 0.02. So that means that this particular space warp has a much higher frequency. So let's have a look what happens when we implement the first force, the first wind with the large curves, and we'll see how that actually plays back in the viewport. So I'm just going to turn off this force and turn on the first one, go into the viewport and press play and see what happens. So there you go, you can see the particles are flying off through space, and you can see